All right, let's get right into it. We're about to explore a war that's being fought not with chemicals or with fly swatters, but with numbers, with data, and some seriously powerful equations. This is the incredible story of how math is becoming our single greatest weapon against one of nature's deadliest creatures.
You know, that question really gets to the very heart of what we're talking about today. For decades, the fight against mosquitoes in Africa has just felt like this constant uphill battle. But what we're seeing now is a complete shift in strategy, a radical one, where the heroes aren't just biologists in a lab, they're mathematicians.
Okay, so before we can even get to the solutions, we first have to wrap our heads around the sheer scale of the problem. We're dealing with an invisible enemy that takes a truly devastating toll every single day.
Now here's the thing. This isn't just about malaria anymore. I mean, don't get me wrong, malaria's impact is absolutely staggering. But now we're facing a war on multiple fronts. We've got these emerging threats like dengue, Zika, and chikungunya popping up. The battleground itself is expanding, and the stakes, well, they just keep getting higher.
And this right here, this is the new frontier. It's a conflict fought with data points, with algorithms, with predictive models. See, to defeat an enemy this complex, you have to learn to think like it, to predict its next move. And that is where the math comes in.
So how in the world do you create a blueprint for something as, chaotic as an epidemic? Well, it all starts with a single, unbelievably powerful number.
Say hello to R0. The easiest way to think about it is like a viral social media post, right? If, on average, every single person who shares it causes more than one new person to share it, that post just explodes online. That's an R0 greater than 1. But if it's less than 1, it just fizzles out and disappears. For epidemiologists, getting that R0 number below 1, that is the entire game.
But R0 doesn't just appear out of nowhere. It's fed by this incredible data pipeline. It all starts on the ground, with real-time reports coming in from local clinics. That raw data is then crunched together with all these complex variables, like how people are moving around and what the weather patterns look like. And the result? A forecast that can actually predict an outbreak before it even happens.
Okay, so we can predict an outbreak. That is amazing, right? But prediction, that's only half the battle. So how do we actually turn these forecasts into real protection for people? Well, that's where the math of intervention comes in, translating all that data directly into life-saving action.
Let's take insecticide-treated bed nets, for example. We all know they work, but math helps us figure out exactly how well they work and, crucially, where they're going to have the biggest possible impact. It's all about optimizing their deployment to protect not just one person, but entire communities, all to push that R0 number down.
And now we're getting into stuff that is seriously cutting-edge science. Gene drives. This is a revolutionary technology. It's designed to guarantee that a specific genetic trait, say infertility, gets passed down, spreading like wildfire through a mosquito population. The math behind this is just mind-blowingly complex, modeling how this genetic takeover is going to unfold over generations to hopefully crash the entire population.
So, a huge part of this is just about being more efficient. Instead of just blanket spraying an entire area which is wasteful and can damage the environment, these mathematical models can pinpoint the most critical mosquito breeding grounds. This allows for targeted, precision strikes with larvicide, getting the maximum impact while using the minimum amount of resources. It's just smarter.
Everything we've talked about so far is an incredibly powerful response. But the ultimate goal, the dream, is to move from just reacting to an outbreak to preventing it from ever getting started. So the big question is, how do we actually get ahead of the swarm?
Well, the answer lies in predictive technology. The best way to think of it is like a weather forecast, but for disease. We've got AI that can scan satellite images, looking for these tiny environmental changes that signal a perfect mosquito breeding ground is about to form. Then, machine learning takes all that data and tells us the absolute best way to distribute our resources: nets, sprays, medicine, for maximum impact. It can even give us an outlook years into the future.
But listen, all the data, all the AI in the world, it's completely useless without one final, absolutely critical component. And that is the human element, the people on the ground. And this slide just shows perfectly why that's so important. You can have the perfect mathematical solution, but if you just force it on a community without their input or understanding, it's going to fail. Trust is low, people don't participate. The models that actually succeed are the ones co-developed with community leaders. That local buy-in, that trust, it's the ultimate variable that makes the entire equation actually work. Of course, with this kind of incredible power comes profound responsibility.
Technologies like gene drives and mass data collection, they aren't just scientific challenges, they're massive ethical ones. The trust we just talked about hinges completely on deploying these tools responsibly, transparently, and always with the consent of the communities they're meant to help. It is a totally non-negotiable part of the equation.
So, here we are. We have the tools, we have the mathematical models, the predictive AI, the targeted interventions. The equation for a future free from these devastating diseases is literally being written as we speak. The only real question left is, what part will we play in solving it?